Good afternoon, everyone. My name is Greg Boyer, and I am the Marketing Manager for Hosokawa Micron Powder Systems. We'd like to thank you for attending our webinar on basics of dry powder classification. Let me point out, if you have any questions during the presentation, you may submit your questions online at any time. Please refer to the Q&A pane on the right side of your screen. At the conclusion of the webinar, we will try to accommodate as many questions as possible. Hosokawa Micron Powder Systems is a division of the Hosokawa Micron International Group. Our parent company, Hosokawa Micron Corporation, is headquartered in Osaka, Japan. We are the global leader in powder processing equipment and systems with 8 operating units and 6 sales offices around the world. We have over 1,500 employees worldwide, production facilities in 5 countries, and 12 technical centers with state-of-the-art research facilities. We encourage our customers to visit our facilities where they can partner with us to develop new materials and processes on more than 30 different pilot and production lines for size reduction, classification, mixing, drying, and many other technologies. Hosokawa Micron Powder Systems, founded in 1923 under the name Pulverizing Machinery, is responsible for Hosokawa's business in North America. From our Summit, New Jersey facility, we provide full sales, testing, engineering, manufacturing, and aftermarket services for the food, pharmaceutical, chemical, and mineral industries. We have both chemical and pharmaceutical technical centers and contract manufacturing facilities. We are the proud inventors of the micropulverizer, hammer and screen mill, as well as the micro ACM, the most versatile air classifying mill on the market today. Our brand names include Micro, Alpine, Riconata, Majak, Micron, Hosokawa BPEX, Stott, and Vital Air. At this point, I'd like to hand the presentation over to our presenter, Rob Voorhees, Vice President and General Manager of Hosokawa Micron Powder Systems. Rob has over 30 years of experience in the powder processing industry. He holds a BS in Industrial Technology from Montclair State University and has completed the Executive Management Program at Tuck Business School and Dartmouth University. Rob holds several design patents for new size reduction and classification technologies. He has been the Vice President and General Manager of Hosokawa Micron Powder Systems since 1998. Rob?
Thank you, Greg. Good afternoon, everyone. For the next 35 minutes or so, we will cover the basics of dry powder classification. We will talk about several different types of classifiers and their application. We will also discuss some classification theory, and we will look at how classifiers are used as part of a powder processing system. Classification and separation of materials is not a new concept. Various forms of classification have been in existence for thousands of years. Significant developments in equipment and machine design over the last 150 years have allowed for the improvement of separating and classifying powders. The end result has been to improve the ability to control the desired separation point, or as we now call it, the cut point, and to optimize the yields of the coarse and fine fractions. Equally as important is the ability to produce high-quality products on a repetitive basis. Classification is the process of separating or dividing a given material into multiple fractions quantified by its distinguishable property. The most common property being particle size, where we separate larger particles from smaller particles. Another property would be density, separating heavier particles from lighter ones. Particle shape is yet another property for separation. As an example, the separation of spherical particles from plate-like particles. Unfortunately, separation by shape is normally very difficult to accomplish. Most commonly, the fines fraction is usually the end product, and the coarse fraction is discarded, or as an example, the coarse fraction could be returned to a mill for further size reduction. There are some applications where the end goal is to dedust the product. In this case, the coarse fraction is the end product, and the fines are discarded. There are numerous methods available for classifying dry powders, so we will begin by categorizing these methods by equipment type. Mechanical sieves can be used in various styles to screen or sieve powders through perforated or woven screen sheets with different opening sizes. Crude separation of powders can also be accomplished with cyclones. This is a good solution when only fine particles are to be removed. Gravity classifiers use gravitational force, weight, to create a force on heavier particles, separating them from lighter particles that are more susceptible to the force created by airflow. Separation by gravity can be accomplished for cut sizes in the range of 200 microns up to several millimeters. For cut sizes of 200 microns down to 1 micron, dynamic classifiers are required. Above 150 microns, mechanical screeners are usually the most efficient and cost-effective method for classifying dry powders. Dynamic classifiers use a centrifugal force developed by a rotating classifier wheel to oppose the centripetal force created by opposing airflow to separate particles. The most flexible and efficient type of technology for ultrafine classification is the dynamic air classifier. The dynamic air classifier uses the forces we just mentioned to split the powder into two fractions, one fine and one coarse. It's important to note that when separating particles below 10 microns, the energy required to overcome van der Waals forces becomes significant. In these applications, high energy dispersion classifiers are required. Let's spend some time to talk about terminology used in classification. Throughput is usually defined as the mass flow rate of material through the air classifier. Throughput of a classifier primarily depends on the airflow and the classifier wheel size. Higher airflows and larger classifier wheels can provide higher throughput. Yield is the measure of the product collected, irrespective of quality, and is calculated as a percent of product, fines or coarse, to the total feed amount. The next term is classification efficiency. Classification efficiency is the measure of the percentage of the fines or coarse being extracted from the feed material. The exact value of the efficiency might change depending upon the values being recorded. Cut size is probably one of the most important terms when defining your separation requirement. It is the point of actual separation defined as the particle size that is found to have the equal probability of being in both the fines and coarse fractions. Cut sharpness, on the other hand, requires some additional information in order to make a calculation. In generic terms, indicates how effective the classification is and indicates how much of each fraction's size distribution overlaps the other classification. In a very sharp cut, each fraction contains mainly the particles above or below the desired cut size. Another relevant term is the load factor. The load factor is defined as the mass of feed in pounds or kilograms per the total mass of air utilized. It is an indication of the energy effectiveness of a classifier, and this will have a direct impact on the cost of classification. The higher the amount of air required to move a fixed amount of feed material, the higher the energy required, and hence the higher the cost of operation. Here we're looking at a density distribution curve, and we can see the point of intersection of the fines fraction and the coarse fraction curve locates the cut size. Just to make it clearer, this is the overall particle size distribution. Here we have the fines fraction, and here we have the coarse fraction, and here we have the overlap, and the actual median value of separation curve is indicated here as x50. This is also the targeted particle size where the separation of the fines and coarse segment are desired. So when we're talking about a cut size of 50 microns, we're trying to split our feed material into two streams, with one segment of particles that are smaller than 50 microns and the other segment of particles that are larger than 50 microns. Also, by theory, half of the 50 micron particles will be in the fines fraction and the remaining half will be in the coarse fraction. There are several different ways of defining cut point, and although the one above is the most common, there is an analytical cut point as well as an overlapping cut point. Here we can see how to define an overlap cut point marked as XU on the graph. The intersection of the coarse distribution curve and the 1 minus cumulative fines distribution curve indicates the particle size where the percentage of undersized particles in the coarse fraction is the same as the percentage of oversized particles in the fines fraction. Here you can see the coarse fraction curve and the 1 minus cumulative fines curve, and XU, which marks the overlap cut point, and the amount of particles in both fractions that overlap both the fines and coarse are shown here. Very good classifiers can operate with an overlap value of around 10%. However, in most industrial applications, the overlap is higher in the range of 20%. It can even be as high as 30% when higher loading factors are employed to maximize capacity. Targeting cut point sizes below 10 microns will also have a negative effect on the sharpness, causing larger overlaps due to the higher interparticle forces in fine powders. This slide shows a grade efficiency or sharpness curve. We were looking at the ratio of particle sizes D25 over D75. So this point, D75, and this point, D25. This ratio will indicate the sharpness of the particle size distribution. Basically, we're looking at the slope of the grade efficiency curve. Sharpness is often used to quantify air classifier performance. Particle size distribution sharpness values range from 0, almost no classification, to 1, ideal but not really achievable in practical applications. In a production environment, an air classifier's cut sharpness ranges between 0.3 to 0.7. At low classifier loads, the cut sharpness can reach values of up to 0.9. A good classifier can achieve a very fine cut size with a high degree of sharpness. I wanted to review a classification example with you to make the understanding of some of the technology clearer. Here's a classifier that's being fed with a material at a feed rate of 100 pounds per hour. The cut point chosen for this application is 30 microns. So operating parameters of airflow and classifier speed are set to achieve this cut point. First, we analyze the feed and find that in the 100 pounds of feed material, we have 40% of the material below 30 microns and 60% of the material above 30 microns. After classification, the fines fraction contains 30% of the original feed material, with 83% or 25 pounds of the fines fraction being below 30 microns and 17% or 5 pounds of the fines fraction being above 30 microns. In this case, the fines yield is 30%, and the efficiency is defined as the amount of below 30 micron material in the fraction divided by the total amount of below 30 micron material in the feed material. In this case, 25 divided by 40 gives us an efficiency rating of 62.5%. A similar calculation can be done to achieve the same information for the coarse fraction. Here you can see the efficiency on the coarse yield is much higher at 91.5%. This slide shows the numerous classification technologies offered by Hosokawa. Many of these classifier types are also offered by other process equipment manufacturers. The chart clearly shows the particle size range capability of each classifier type, as well as the markets in which they are utilized because of their design parameters. While in several cases the classifier type carries over into more than one market, the design and construction of the classifier is usually very different to accommodate the requirements of the particular industry. The first technology we'll discuss is the mechanical separator. The mechanical separator works via a mechanical screening or sifting technique. This technology uses a wire mesh screen with different opening sizes to separate a given product into two or more fractions. There are two basic types of screeners available in the marketplace. The gyratory type screener that is pictured in this slide is available with a wide selection of options. It could come with multiple decks with different screen sizes in each deck, starting from the top with coarse screens to the bottom with finest screens. This configuration will allow the incoming feed material to be separated into multiple fractions from coarse to fine. These units are particularly suitable to classify free-flowing powders with a low angle of repose. Vendors offer a range of screening motions and amplitudes to effectively move the material over the screens. Depending upon placement of the unbalanced load, different types of motions can be created. These devices usually can operate with a 90 to 95% efficiency, which makes them very attractive options in applications where they can be utilized. One of the major drawbacks with this type of classification device can be the blinding of the screens. This can result in significant degradation of sieving performance. Therefore, a number of different screen cleaning devices have been developed. Some of these options are balls or discs that bounce under the screen to cause additional impact from the bottom up to dislodge particles and keep the screens clean. Another option is reverse airflow, which could consist of a sweeping arm that can blow air from underneath to keep the screen clean. Brushes, ultrasonic devices, or combinations of the above can be used to keep the screens clean and make the screening process more efficient. There are a couple of additional terms worth mentioning when discussing classification in general. The first term is scalping. Scalping means the removal of a small percentage of coarse material that could be in the feed material. The second term is dedusting. Dedusting is just the opposite and means that a small percentage of the fine material is the undesired fraction that needs to be removed from the feed material. Another type of mechanical screening device is a centrifugal screener or rotary sifter. These units are typically used for materials with more difficult flow properties and when higher throughputs and capacities are required. This device uses a cylindrical wire mesh or cloth screen of a specific opening size to control the cut point. Within the screen, a rotor is used to mechanically disperse and centrifugally force the material to the screen, with the fines pass through the screen into the fines outlet. The coarse material travels horizontally to the end of the screen where it is discharged through a separate coarse outlet. This type of screener is more suitable for applications where the coarse fraction is not significant, typically in the 10% range or less. One shortcoming of this technology compared to screening deck we saw on the previous slide is that these units will only allow for one single cut or separation point at a time. This slide shows a typical mechanical screening system. Feed product is uniformly introduced to the screener through a centrally located product inlet from a volumetric feeder. In this case, the screener has one screen which provides for the separation of powder into two fractions. Here, the coarse fraction is shown discharging from above the screen into a drum on the left, and the fines fraction is discharged from the bottom of the screener to another drum on the right. Mechanical screening systems like this are most effective for separations above 150 microns. In some cases, it can process finer materials that have very good free-flowing properties. The separation principle at work in this device, called a cyclone, is what is known as a free vortex. The feed enters the housing tangentially in a high-velocity airstream, typically in the range of 30 meters per second, as shown here by the red arrow. The air is then put into a spiral motion and continues downward due to the location of the center outlet or fines discharge tube shown here. The circular airflow movement forces the larger particles to the periphery of the housing and then down to the coarse outlet at the bottom of the cyclone. The airflow draws the finer particles inward toward the fines outlet. By varying the airflow, air velocity, and cyclone dimensions, the cut size and collection efficiency can be maximized to a certain extent. These devices are very efficient in collecting particles that are larger than 10 microns. Their efficiency starts falling off as the particle size gets smaller. The major problem with cyclones is their inability to control the cut point. This being a simple device with no moving parts results in it being a very economical solution for some applications. This device can also be used as a primary collection device due to the same beneficial features mentioned earlier. This graph shows a collection efficiency curve for a typical high-efficiency cyclone. It can be seen very clearly that above 10 microns, the collection efficiency is well above 95%. Here you can see the 10 micron particle size distribution. And here you can see that it's above 95% above or efficient above 10 microns. One of the parameters that affects performance is the diameter of the outlet tube. By reducing the outlet tube diameter in a cyclone, the effective outlet vortex will be reduced, causing an increase in the collection efficiency of finer particles. The downside to this improvement will be the increase in the pressure drop across the unit. While a typical cyclone will work with a 6 to 8 inch water column pressure drop, a high efficiency unit can reach pressure drops as high as 15 to 18 inches. Due to their very simple construction, it is also fairly easy to design them for high pressure ratings to handle materials that can present potential explosion hazards. I would like to add that with most high efficiency cyclones, you will find an additional chamber or dust trap under the conical section of the main cyclone housing. This additional chamber will minimize the chance that the product being discharged will get re-entrained into the center vortex, hence improving the collection efficiency. The simple design of these units makes them easy to troubleshoot as well. The primary reason for poor performance in a cyclone would be a possible air leak in the sealing device placed on the coarse outlet. If a low-end airlock is used with high leakage rates, there will be a distinct drop in the performance of these units. This is because the airflow due to the leakage will re-entrain the coarse particles back into the fine stream. A dynamic classifier can be incorporated into cyclones, like the unit shown in this photo. The addition of a classifier provides a cyclone with much improved cut size control. This slide shows a simple size reduction system where coarse material is discharged from a rotary granulator and then air. In this case, the collection efficiency of the cyclone is very high, eliminating the requirement for a dust collector for the fine material collection. The minimal amount of fine material that passes through the cyclone is easily collected in the filter sock shown here on the discharge of the material handling fan. The low dust loading requires only periodic emptying of these filters. Filters are shown here. Gravity classification, also referred to as elutriation, relies on the drag force of the gas imparted on the particles by Stokes' law to provide the separation function. As can be seen from the formula for the drag force that is trying to move the particles in an upward direction, the magnitude of the force is directly proportional to the cross-sectional area of the particle, AP. This is the formula for drag force. The drag coefficient, density, and gas into the second power of the velocity. Conversely, the opposing force that is trying to move the particles in a downward direction is the weight of the given particle. This is obviously associated directly with the volume of the particle and the density of the material. When these two opposing forces equal each other, the subject-sized particle theoretically will be in suspension, and by further altering this equilibrium and changing the parameter discussed, we can decide which particles are going to be conveyed upwards, which will be the fines fraction, and which particles will fall downwards, which will be the coarse fraction. Unfortunately, there is a small problem with this concept. When you have particles of the same size, but with different densities, or particles that weigh the same, but have different surface areas, separation performance is adversely affected. The gravity air classification system shown here is based almost entirely on elutriation. It has a zigzag-shaped classifying channel to improve classification. Air enters at the bottom and feed enters near the top. The air carries the fines upward against gravity and out the top, and the coarse particles drop by gravity and exit at the bottom. This type of classifier provides gross classification in a size range that can also be accomplished by sieving, but also works for materials that cannot be effectively sieved. This type of system can also be effectively used to dedust products such as plastic granules, fibrous materials, and separation of leaves, sticks, bark from spices, and other dissimilar density materials. These types of classifiers are capable of separations in the 0.3 to 10 millimeter size range. Here's a closer look at a production type machine that works on the elutriation principle. As with all air classification techniques, the most important parameter in achieving a good separation is the proper dispersion of the feed material. It is not practical to achieve acceptable efficiencies in gravity classifiers with straight pipes due to the laminar boundary layer of air that develops at lower velocities. To circumvent this problem, zigzag channels have long been employed in the designs of these classifier types. The zigzag profile offers several advantages. Particles that slip down along the walls become caught up again in the flow at every turn of the channel. The zigzag classifier can therefore be regarded as a device with many separation zones. This gives the classifier a high separation efficiency in its operational range. The production unit pictured here is fed closer to the bottom of the classifier. Coarse material gravitates downwards against the airflow, and the fines are conveyed upwards and are collected in a cyclone. The production unit shown here can achieve capacities of several tons per hour and higher. The typical load factor for zigzag classifiers is in the range of 1 kilogram of material per 1 kilogram of air. The next few slides show examples of classifiers that have a dynamic classifier wheel. These classifiers work on the induced vortex principle of classification, and in addition use a secondary classification principle based on elutriation. The combination of both separation principles gives us a classifier that provides the highest efficiency and produces the best yields. This particular classifier design provides classification in the range of 15 to 150 microns at relatively high capacities. Due to the medium speed range of the classifier wheel, the advantages of a lower pressure drop across the unit and lower wear rates are achieved. As shown by the arrow, both feed material and air enter at the bottom of the classifier and are drawn upward toward a vertically mounted classifier wheel. The rotating wheel creates a force vortex where the airflow draws the fine particles through the rotating wheel, and the coarse particles are rejected by the centrifugal force generated by the rotating wheel and fall by gravity to the coarse discharge at the bottom of the unit. As the coarse particles fall downward, they pass through a zone where secondary air is induced tangentially into the classifier. This additional air is used to wash and disperse fine particles from agglomerated coarser particles and return them to the classification zone. This classifier is similar to the type of unit we just discussed. These classifiers can also be fed by gravity, either from the side or the top as shown here, or alternately, material can be pneumatically conveyed into the classifier from the bottom. These classifiers can provide classification in the range of 3 to 100 microns. In either instance, there's always a secondary air inlet where a fraction of the total flow is used for particle dispersion. Dispersion is one of the most important criteria for efficient classification. There are numerous designs of guide vein rings to improve the separation of fine and coarse particles. When pneumatic conveying is the means of introducing the feed to the classifier, the split of airflow between the feed and the air dispersion line is usually 50-50, but can also be variable for fine-tuning the classification process. Air classifiers which are fed gravimetrically from above can operate with high load factors, up to 2 kilograms of material per kilogram of air. Air classifiers which are fed pneumatically from below often only achieve load factors of around 1 kilogram of material per kilogram of air. This value can drop further when there are increased demands on product sharpness. The incorporation of multiple wheels in the classifier design provides some significant advantages over single-wheel classifiers. Each smaller wheel can now handle a portion of the total airflow, so on larger systems where higher airflow is required, these units can provide significantly higher capacities. Since a smaller diameter wheel can rotate at higher speeds, finer cut points can be achieved at these higher throughputs. As an example, we show both a single wheel classifier here and a multiple wheel classifier here for very large high capacity applications. This is an example of a dynamic classifier incorporated into a production system. The basic components of feeder, product receiver, and fan are all shown here in a standard system arrangement. This system is designed to handle materials that present a potential explosion hazard. Here, all system components are designed for the overpressure generated by an explosion. The air and material entry and exit points of the system are provided with valves that close under pressure and isolate the explosion within the system, protecting personnel and the environment. And you can see the barrier valves located at the inlet and the exhaust of the system. I wanted to briefly mention another variation of a dynamic classifier known as a closed-loop air classifier. The advantage of this type of classifier is that there is no need for additional ancillaries like a fan, cyclone, or dust collector to complete the system. This type of classifier can stand alone. The mode of air is generated by an internal fan that circulates the air within the main housing, indicated as shown here in the blue loop. This helps in dispersing the material while carrying the particles to the dynamic classifier wheel shown here in yellow. The finer particles that pass through the classifier wheel are directed to the outer housing and flow downward for discharge, while the coarse will be discharged through the inner cone and out the bottom side outlet. There are some limitations to this technology. The achievable cut point is usually not very fine, typically in the range of 45 to 150 microns, and not as sharp as some of the high-efficiency classifiers we discussed. These units are also large in size, and due to additional internal dispersion veins and other components, are not very suitable for regular cleaning. On the other hand, they offer a lower capital cost than conventional systems and have a low specific energy consumption. Cut point is adjusted via a change in the classifier wheel speed and or fan speed. This slide shows a multi-wheel classifier installed as part of a complete ball mill grinding system. The multi-wheel design provides a fine product cut point at high capacities. Large capacities are typically required for large minerals processing systems. In this system, the coarse material ejected from the classifier is returned to the mill for further size reduction. The combination of a high-efficiency classifier and state-of-the-art controls provides for a superior performance in these types of size reduction systems. This slide depicts a size reduction system with secondary classification capabilities. It also includes a cyclone for secondary product collection and a mechanical screening deck used as a safety system to scalp off out-of-spec material. In this system, a mechanical impact mill provides the size reduction capabilities for the application. The mill's internal classifier provides top size control of the particle size distribution. The inline classifier, which is close coupled but downstream of the mill, provides the bottom cut, which is the removal of the fines from the particle size distribution. This combination of classifier mill and inline classifier provides for a very steep particle size distribution. So here you can see several of the technologies that we discussed. Here you can see several of the technologies we discussed. The inline classifier, the cyclone, and the screening deck, all incorporated into one system. The two types of classifiers just shown utilize a dynamic classifier wheel. The principle of operation here is the balancing of the drag force, which is trying to move the particles through the wheel, with the centrifugal force opposing it, which is created by the rotational speed of the wheel. By equating the opposing forces of FD and FA, shown here, the basic formula for cut point size determination can be derived. This formula is based on the assumption that the particles are spherical, so depending upon the structure of the particles, additional multipliers can be introduced to compensate for the variance of the drag force. It is also worth talking about some of the design variations available for classifier wheels. The image here shows a classifier wheel with canted blades, rather than the typical radial blades that are more commonly seen in classifier wheel design. The advantage of such classifier wheel is that it will prevent particle scatter caused by the vortices formed on the trailing side of the blades, hence providing a sharper cut. Additionally, an insert tube or an orifice can be utilized with these types of wheels to create a stronger internal vortex to achieve even finer classification. The downside to both of the modifications mentioned is that they will cause additional pressure drop, which will result in a higher energy consumption and an increase in operational costs. It's critical to note here that the effective rotational speed of the wheel, the term VU, shown here, is to the second power versus the linear effect of the drag force, which is represented by the term VR. Here you can see the effect of the peripheral velocity on the outcome of the cut size. In most cases, airflow is used as a means of increasing capacity as long as the classifier speed required to achieve the desired cut point is within the operational limits of the classifier and drive. On the other hand, reducing the airflow could enable a classifier to produce finer cut points, though the highest effective speed of the classifier wheel is reached. Looking at this formula, you can see that a small change in rotational speed of the wheel will have a much more significant effect on the particle size cut point than that of the airflow. One additional variable that can be considered is an extended length classifier wheel. By increasing the length of a given classifier wheel, the enlarged surface area of the wheel allows for a radial velocity to be lowered, resulting in a reduction of the drag force and therefore producing a finer cut. We can summarize the variables that affect the performance of a classifier as follows. First, classifier wheel speed. Higher wheel speeds produce finer cut points, and lower wheel speeds produce coarser cut points. The second parameter is air volume, where lower air volumes produce finer cut points, and higher air volumes produce coarser products. And lastly is feed rate, where lower feed rates create sharper cuts. The next few slides will show the effect of each parameter in more detail. Here you can see a graph showing the effect of classifier speed on the cut point. As the wheel speed increases, the cut points get finer. From the three separate curves shown here based on material density, it's also clear that it's easier to classify denser materials. This can clearly be seen in the formula shown in the earlier slides, where the effect of the centrifugal force will be more prevalent on smaller but heavier particles, while the effect of the drag force on particles will be less, since it is only associated with the cross-sectional profile of the particle. With lighter density material, there can be a tendency for material to float around the classifier wheel, causing high motor currents and scattering of coarse particles through the classifier wheel due to overloading in the classification zone. The result will be a reduction in sharpness. In this slide, we can see again the effect of airflow on particle size. Aside from the fact that we can achieve finer cut points with lower airflows, we can also see the effect of a change in classifier wheel speed. With classifier tip speeds around 60 meters per second range, we can see that the change in airflow has a much more significant effect than when the blade tip speeds are doubled. This graph clearly illustrates the pronounced effect of classifier wheel speed on the cut point versus the effect of airflow. Here we can see the effect of feed rate on particle size, where the reduction in feed rate generally provides for a finer cut. More significant is the change in sharpness of cuts that can be achieved. This graph shows that an 8-micron cut point, when the feed rate is increased to around 100 kilograms per hour, the sharpness reduces drastically. This means that there will be a significant carryover or overlap in the final product fraction. One additional observation can be made from this data is that a large change in cut point can take place if the feed rate is not controlled uniformly on the lower end of the finest scale. If we try to quantify this from the graph, we can see that while 1 kilogram per hour change in feed rate might not have any effect on the cut size in the upper end of the feed rate range, the same amount could mean a shift of upwards of 30% in the lower end of the feed rate range. This is yet another type of classifier designed for medium fine separation in the range of 20 to 200 microns. This classifier operates a little differently than the types of classifiers we have previously discussed. The central gravity feed and distribution plate provides uniform product distribution to the classifier wheel, allowing for precision cut points and high fines yields at lower airflow rates. The classifying air enters the housing tangentially and flows through a guide vane ring where it is dispersed uniformly to the classifier wheel, improving classification performance. The fines are removed as the material moves downward into the classifying zone, and the fines are entrained in the exiting airstream and leave the classifier. The coarse material is rejected by the classifier wheel and drops to the vertical discharge at the bottom of the classifier. These classifiers can be operated as a once-through system or as a closed-circuit system, with a cyclone returning the discharge air back to the classifier. These units are very compact and can be completely wear protected, making it an especially good choice for minerals processing applications. They can operate at high throughputs with low pressure, overall pressure drops for low energy consumption. This ball mill system uses this type of classifier in a closed loop circuit system design. Product discharge from the mill is lifted by a bucket elevator to a safety screener. From there, it is gravity fed to the classifier. You can see that product collection is accomplished by a cyclone, and the classifier air system is recirculated back to the classifier from the discharge of the fan. It can clearly be seen here the compact and energy-efficient design of these classifier systems. For superfine classification of difficult materials that require very high energy for dispersion and separation, the classifiers shown here can handle these difficult types of classification applications. This classifier uses a very small dispersion air gap around the classifier wheel to introduce high-velocity air for optimum particle dispersion and separation. This unit can classify particles from 1 to 50 microns. It can provide very tight particle size distributions with a sharpness index of between 0.7 to 0.9 for a wide variety of materials. This unit can provide extremely efficient classification in bottom cut applications between 4 to 10 microns. Due to this classifier's high energy dispersion characteristics, it's also used for classifying high aspect ratio materials which separate better under high energy dispersion. The unit shown here is a laboratory scale system capable of cut points from 0.5 to 35 microns with capacities of up to 20 pounds per hour. Production scale systems are available for capacities of up to 4,000 pounds an hour. The latest development in classification is a new special machine designed for research, development, and laboratory use. It is designed for processing the smallest samples with the highest possible yields. The purpose of this machine is to duplicate larger technology in the smallest possible scale. It is a small-scale extension of the larger dynamic classifiers discussed earlier in this presentation. This classifier has a 20-millimeter diameter wheel. To duplicate the tip speeds of the larger units, it can run up to 60,000 RPM. The feed sample size can be as small as 5 grams for this unit. Here you can see the classifier mounted on a common base with common controls that are used to operate a series of different powder processing equipment. In addition to classification, this one basic control and powertrain module can handle 5 different basic processes and 9 different powder processing machines. This concludes the presentation today on basics of dry powder classification. I hope you found it informative. Thank you very much.
Thank you, Rob. At this point, we'd like to start our question and answer session. As we may have noticed, we've gone a little over time, so we're only going to take a few questions today. But I would like to remind you, if your question is not answered during the Q&A session, Rob or someone else from our company will contact you offline. First question is, can you please explain again the difference between yield and efficiency?
Okay, we did have a slide on this topic. Yield and efficiency are different, and they are calculated differently. Early in the presentation, I gave an example that you can go back and refer to. Just to summarize, again, yield is the amount of material in either the fines or coarse fraction that is a percentage of the total feed. Efficiency is a measure of how well the classifier performs the separation. The efficiency is the percentage of material in the fines or coarse fraction that's within the desired cut point measured against the amount of material within the cut point of the feed. I hope that answered your question.
Okay. Next question. What is the basis for sizing a cyclone?
Cyclones are installed as part of as part of a powder processing system, and they're usually sized based on the airflow requirements of the system. That's the most important parameter for sizing the cyclones.
Okay. Next question. Can you please explain how material loading affects classifier performance?
Again, we discussed this topic a little bit. Classifier loading can affect the performance in several ways. But loading is often adjusted to achieve the optimal performance with respect to sharpness of the cut. Since classification depends on good dispersion of particles for efficient classification, a lowering of the loading factor will allow for better interaction between individual particles and the dispersion air, ultimately yielding a better separation.
Okay, we have time for probably one more question. We'll just see if I can find one that's probably easier. Can any of the classifiers mentioned in the presentation be used with an inline mill?
The answer is no. If the intention is to use a single source fan to provide induced draft for milling system, then not all the classifiers we mentioned today will work with this type of system. There are specific classifier designs that use very low amounts of secondary airflow for washing and elutriation. We did talk about those briefly. These classifiers are much better suited for inline systems, as it's basically easier to balance the airflow requirements of both the mill and the classifier when the total airflow requirement of the mill is constant and not divided between the mill and the classifier.
Okay. Well, thank you once again, Rob. Like we said, if we did not have a chance to answer your question during the presentation, we will respond offline by email in the next day or so. Please continue to check our website for future educational programs, and feel free to contact Rob using the information provided above. Today's program has been recorded and will be posted online within about 48 hours. We will email everyone who participated today a link when the file becomes available, so please feel free to share this with your friends and colleagues. We'd like to thank you for your participation once again, and have a great day.